Hello and welcome to section 14 of this course. In the previous section we talked about time series analysis. In this section we'll explore some geostatistical interpolation methods. As always, the first video is dedicated to provide you with some theoretical background for the techniques we're going to learn in the section. For this experiment we're testing some deterministic estimators and then Kriging interpolation. This video will talk about the basics of these methods. The aim of geostatistical analysis is very simple. It's creating maps. Let's say, for example, that we need to map the spatial pattern of wind speed for an entire century. Clearly we cannot place measuring stations on a dense grid or across the country because this would be too expensive and very unpractical. Since we cannot cover the entirety of the study area with sampler, we need to find a way to map our variable in a different way. Geostatistics provide interpolation techniques created specifically for such a purpose. The simplest form of interpolation are linear models. In this case, we're simply modelling the variable using a linear of polynomial model based on the coordinates of the points we sampled. Another commonly used form of deterministic interpolation is inverse distance weighted. This method is based on a weighted sum where the value of an unsampled location, the yellow point, is estimated using the weighted sum values of nearby observations, red points. As the word inverse distance suggests, the weights to assign to each of the red points are calculated using the inverse of their distance from the yellow point, raised by p, which is the power index. We'll see later on how this power can affect the results of the interpolation. Probably the better known geostatistical interpolation method is Kriging. Kriging is based again on weighted sums, therefore to estimate the yellow point we're using a weighted sum of the red points. The crucial difference between inverse distance and Kriging is that here the weights are computed based on a statistical analysis of the spatial pattern of our variable. This statistical analysis is represented by the Variogram, where the semivariance, i.e. half the variance of 2 points separated by a lag distance equal to h, is plotted against the lag distance itself. The semivariance can be computed for all pairs of points in our dataset. This is known as the Variogram cloud. The Variogram cloud again plots semivariance against distance, but includes all pair of points. The variogram is simply an average representation of the variogram cloud. Instead of computing the semivariance for all pair of points, we average the semivariance of all points separated by a certain lag distance. Once we have the variogram, we can try to model the semivariance as a function of distance with a method similar to a linear regression. This way we can fit a model to our variogram that allows us to determine a value of semivariance continuously for every possible value of distance. The variogram only represents certain lag distances. The variogram model represents all distances continuously. The variogram model is based on several parameters, which we need to set in the script. These are the nugget, which is the intercept of the variogram on the y-axis, the sill, which indicates the semivariance value at which the variogram becomes flat, and the range, which is the distance at which this flattening happens. From the variogram model we can compute the weights, which in turn allows us to estimate the yellow point, i.e. an unsampled location, using nearby observations. Since Kriging is probably too complex to explain in detail in the limited time available for each video, I included some free resources that you can consult to know more about the Kriging algorithm. Moreover, I also included some resources that show you how to perform Kriging in R using both the package gstat, which we're going to use here, and GeoR. This concludes the first video of the section where we talked briefly about some important theoretical concepts that you need to understand the exercise.